So what? Let's first of all see what this theorem says. So this theorem says that if we have three functions f, g, and h, such that this particular expression, sorry, that this particular expression holds, that this particular expression holds for all x in the common domain of the definition. So here we mean that if, let's say, function f1 is defined in the domain d1, g is defined in the domain d2, and h is defined in the domain d3, then if we have the intersection of these three domains as d1, d2, d3, we'll take this, in this domain we'll try to apply the sandwich theorem. So if this expression holds in the common domain, then for some real number a which lies in this particular domain, that is a epsilon d, we'll have limit as x tends to a fx equals to L, and the limit x tends to a hx, then the limit of gx will also be equal to a. This particular thing is more intuitive if you work geometrically. Let's say we have three functions. This is f, this is fx. Let's try it with another color here. So we have let's say this is hx, okay. To draw gx, let's take green color. So we have this was hx, sorry, this color. So this is gx. So basically, let's mark this also. We have this as hx, this is gx, and this is fx. So at this particular point, that is x is equal to a. Let's revert back to so at this point, what we have is that limit of fx is equal to L, and the limit of hx is also equal to L. So since hx and gx are the upper and the lower boundary of gx, so as you can see, as x tends to a, closer to a, we'll make the value of these three functions closer, and eventually as x tends to a, that is when it's very close to a, we'll have the value of these three functions as equal. So basically you can see that the limiting value of these three functions will become equal. So after we have proved the sandwich theorem, this particular theorem is of primary importance is to be proved. So to prove this, first of all we require to prove this identity. This particular identity has a very beautiful geometrical proof. So let's look into how to prove this. So to prove this, let's draw this circle of unit radius and make certain constructions. So let me first of all tell what are the construction. So first construction is we take an arc of, say, which subtends an angle x at the center. Second, we have this particular line CD dropping perpendicular to the line OA. So we have CD perpendicular to OA, and then we draw AB perpendicular to OA such that if we extend OC, it intersects this particular line at B. So basically we have OAB angle as 90 degree and angle ODC as 90 degree, and these particular things are basically this is equal to 1. So as you can simply note that area of the triangle OAC will be less than area of the sector OAC, and which in turn is less than area of the triangle OAB. So by using this particular expression, we'll can derive the earlier relation. So first of all, let's write down the area of the triangle OAC. So to work out the area of the triangle OAC, we'll first of all look into the triangle OCD to find out the length of the perpendicular. So in triangle OCD, we have sine x is equal to CD. Let's say we have CD upon OC. So OC is 1. So we have CD equals, that is length of the perpendicular. Let's say it's P is equal to sine x. So basically area of the triangle comes out to be half base, that is OA, equals to 1 into perpendicular, that is equals to sine x. So this is the area of the triangle OAC. Similarly, let's work out the area of the triangle OAC, which is equal to the angle x subtended at the center upon 2 pi into pi r square, where r is equal to 1. So we have basically x by 2 as the area of the sector OAC. To work out area of the triangle OAB, we have let's see, let's draw the triangle OAB here. This angle is x, we have this as 1, and to calculate the area we need AB. So to calculate AB, let's calculate the tangent x. So tangent x will be AB upon 1, therefore AB equals to 10x. So to calculate the area of the triangle OAB, we have half base, that is OA, is equal into 1 into 10x. So now putting all the plugging on in all the values of the areas, we have sine x by 2 is equal to x, is less than x by 2 is less, which in turn is less than 10x by 2. So basically we have this expression. We can cancel out 2. Now we'll use some of the simple properties of the inequality. So if you don't get, just please revise the inequality chapter. So since we have taken x to be in the first quadrant, that is x lies between 0 to pi by 2, we can see that sine x is positive in this particular domain. Sine x is greater than 0, and if a particular number is greater than 0, we can divide the inequality without any change of sign. So we will have 1 less than x by sine x, which in turn is less than 10x is sine x upon cos x, so sine x cancels out and we are left with cos x. Now we can invert the expression if we just reverse the numerator and denominator. So we'll have cos x less than sine x upon x, which in turn is less than 1 for x between this and this. If you're getting some problem in this particular steps, so let me work out one simple thing. Say we have this particular expression, so we can cross multiply this to obtain sin x upon x is less than 1. Similarly, for the other part of the inequality, you can work out similarly. So we basically have the relation required to prove our identity now. So after we've derived this relation, what we'll see that as x tends to 0, we have the first function, that is fx equals to cos x, tending towards 1, and we have hx, the third function, equals to 1, also tending to 1 as x tends to 0. So basically by sandwich theorem, we'll have the limit of the function gx tending to 1 also. So basically we have limit x tends to 0 sin x upon x equals to 1. This is a pretty important result, and I would like you to just remember its proof also. So let's now work out a simple example of limits to get a feel of what actually we are working with. Here limit x tends to pi by 2. So to solve this particular expression, first thing we do is that we try to convert it into a simpler problem. So to do that, what we'll do is that we'll take x minus pi by 2 equals to y. Therefore, as x tends to pi by 2, we'll have y tending to 0. So the problem will be shifted now to limit y tends to 0, 10 of twice of x minus pi by 2 upon y. So now the question reduces to limit y tends to 0, 10 of 2x minus pi. So we'll have uh, this will reduce to simply 10 to x. Sorry, 10. Basically here we had x, so it'll be plus here. So we'll have 2 pi, 10 of 2 pi plus 2x. So we'll have 10 to x, so 2y. This will be y here. So we'll have 10 to y upon y here. And now to calculate this particular limit, as you see that this particular function is not defined if we put directly y equals to 1. So because it reduces to the form 0 by 0. So we cannot directly put y equals to 0 in this particular limit. So to calculate its limit, we'll use some of the properties which we had learned in the earlier part. So first property is we'll write 10x as sine 2y upon cos 2y into y. And now what we'll do is that we'll use the property of division of two functions, that is if we have this as function and this as another function, so the limit of this particular expression can be written as limit of sine 2y upon y into limit of 1 upon cos 2y. As this limit and this limit individually exists, we'll see if you are not able to get it now. So this particular expression is now defined at y equals to 1. So because cos 2y is equal to 1 at y equals to 0. So basically what we have is that we are reduced to finding the limit of this particular expression only. So to find the limit of this particular expression, we see that it's a bit similar to the expression of the limit we just find out. So to calculate its limit, we'll do another substitution, that is we'll put 2y equals to z here, and as y tends to 0, z will also tends to 0. This particular substitution is absolutely necessary, and do not proceed to the next step before this. So we'll have limit transforming to this, and it will give us sine, let's just rub it. So we'll have sine z upon 2. So now this particular limit, that is limit z tends to 0, sine z upon z is well known to us, is equal to 1. So we'll have the answer as 2.